Fellow mathematicians, we're going to go through a brief review of composite functions, which is an essential topic to understanding the chain rule. Now let's first start by stating the chain rule. We have the standard version written here. And what I want to point out is that the chain rule, this is a differentiation rule for finding the derivative of a composite function. And if you take a look at this version, the composite function is right here, f of g of x. Now, we're not going to focus on applying the chain rule in this video. We'll have that link down below in the description to another video on that. What we want to focus on is, given a function that we'll be calculating the derivative of, how do we identify it as a composite, f of g of x? So let's get right to some notation and our brief review of everything you'll need about composite functions. So first, what is a composite function? A very brief answer. It's where we take one function and plug it into another one. Now the way this is usually written is right here, and that's read as f of g of x. Very common mistake is to interpret this as multiplication. So make sure you realize here, this is not f times g of x, but rather f of g of x. X is first plugged inside of the inner function g, and then g of x is plugged inside of the function f. Now the names that we'll be using here to address the outer and inner functions are standard. We're going to be referring to f as the outer function, and we're going to typically write that as f of x, and we'll be referring to g as the inner function, and we'll write that typically as g of x, both functions of x. Now, some of the examples of functions that we'll be applying the chain rule to are some of these written right here. And in order to apply the chain rule, we're going to have to identify our function as a composite, f of g of x. And that is the most important thing with being able to apply the chain rule efficiently. We want to take one of our given functions. We're going to be calculating the derivative of these eventually. That's going to, again, be linked down in the video below in the description. And we want to be able to identify the outer and inner functions. In other words, we want to be able to identify f of x and g of x for one of our functions here. Now, some of you might be okay on that, but this is a great thing to make sure that you are completely solid on before moving on to some problems with the chain rule. So in the next part, which we'll be getting to in a few seconds, we're just going to take a look at a bunch of functions and identify them as a composite function. In other words, for each function, we'll identify the outer function, f of x, and the inner function, g of x. Let's go ahead and get to that right now. Let's start with a really simple function, y equals the square root of 3x squared plus 1. And what we want to do is identify it as a composite function and write down the outer and inner functions. Now, a lot of students find it easiest to start with the inner function. And if we take a look at our function here, we have 3x squared plus 1 inside of the square root. So let's identify our inner function, g of x, as the inside 3x squared plus 1. Now, once you see that 3x squared plus 1 is inside of the square root, we're going to take our outer function to be the square root of x. Our outer function has to be a function of x. And there we go. Notice why this works if we take g of x, plug it into f. In other words, if we replace all x's in the outer function with g of x, we get our function. So replace x with 3x squared plus 1, we get our function. So this pair works. Now, as it turns out, this is not the only pair that works as a composite function. So let's go ahead and write down a different pair of f and g of x that work. Now, they're not going to be very different from this first choice, but they're technically a different pair. And what we're going to do is take our outer function, and we'll take it now to be the square root of x plus 1. And if you think, what would you have to plug in here for the outer function to give you our function? Well, we would have to plug in and replace that x in the outer function with 3x squared. And there we go. That is a second pair of a function f and g that work, a different outer and inner function. All right, as it turns out, we can give a third pair. Let's go ahead and take our outer function in the second pair here and modify it slightly and get a third pair. And we're going to take f of x, our outer function, to be not the square root of x plus 1, but here we can take it to be the square root of 3x plus 1. And think for a moment, what would you have to replace this x by to get this function? Well, it looks like we'd have to replace x with x squared. So let's take, in this case, g of x, the inner function, to be x squared. And there we go. Now, we have 3 different pairs that work for identifying our function as a composite, but let's think about how we would apply the chain rule. We're going to have to calculate derivatives of our outer and inner functions. And of all these choices, it is only the first that we can calculate the derivative of the outer function. We can rewrite the square root of x as x to the 1/2 power, and we can easily differentiate that outer function with the power rule. So of all these 3 different possibilities, and there are a lot more, this is the pair with the simplest outer function. And that's important to point out, because if you're going to be able to efficiently apply the chain rule, you need to generally have a very simple outer function. And notice in the second and third choices there, you would technically have to be applying the chain rule to calculate the derivative of the outer function here. So you'd be applying the chain rule while applying the chain rule. That's really complicated. We want to go with this first choice. And that's because we can easily differentiate x to the 1/2 with the power rule. We can find the derivative of that outer function no problem. So let's go ahead and make this official and put it on the board. This is really important to being able to apply the chain rule efficiently. And let's go ahead and state it as you want to always use the pair of functions with the simplest outer function. And generally, if your outer function is simple, typically a power of x, that'll be very easy to then differentiate with the chain rule. Now, with that out of the way, let's go ahead and get to a bunch of examples like this, given a function, just identifying the outer and inner functions. And we're going to take a look at a whole bunch of different combinations that are frequently encountered when applying the chain rule. Let's go ahead and take a look at 7 more examples on identifying a given function as a composite. Now, these are all standard examples that eventually you'll be asked to calculate the derivative of with the chain rule. But first, in order to do that, you're going to have to be able to identify the outer function and inner function. Now, if you want, pause the video right now and make an attempt at identifying the outer and inner function for each of these 7. All right, if you're ready, let's go through them. So for each of these, we're going to write down a formula, f of x and g of x, both as functions of x. So let's start with the first one, and this one is rather simple. Notice we have a fifth power on the outside, so we'll take our outer function to be x to the fifth, and our inner function as what's inside the parentheses, 2x plus 1. And there we go. Next, for our second example, we have a fourth power on the outside, so we'll take our outer function to be x to the fourth, and the inner function, that'll be everything in parentheses. And here, that's 5x cubed plus 4x plus 3. All right, third example, we have a 10th power on the outside, so we'll take our outer function as x to the 10th, and our inner function is what's inside the parentheses, e to the x plus 1. All right, you're probably starting to get the hang of this. Things are a little more complicated for example 4 and 5, but we can rewrite them. Remember, that's one of our tips for applying the product and quotient rules. Rewrite before you differentiate, and that still applies here. We can rewrite this as x squared plus 1 to the negative first power. Remember, negative powers, we can understand them as factors in our denominator. Now we're just going backwards, taking factors in our denominator and writing them as factors now to negative powers. And now, this example looks very much like the other ones. We have an outer power of negative 1. So let's take our outer function to be x raised to the negative 1. Our inner function, that'll be the part inside parentheses, x squared plus 1. You can probably see how we're going to rewrite example 5. We're going to think of a square root as being a 1/2 power. A square root in a denominator, we can write that as a negative 1/2 power. So let's rewrite this as 1 plus sine of x, all raised to the negative 1/2 power. And like the other examples, we can take our outer function to be x raised to that outer power, x raised to the negative 1/2. And it's really easy to see the inner function here, g of x, which we would take it to be 1 plus sine of x. All right, next up, example 6. And this is, again, an issue with notation, and you can rewrite this. And we're going to rewrite that with what the power notation means, cosine of x, all cubed. Now, you're going to typically see notation for powers of trig functions written like this, but we understand it as this. So just be careful of that. By rewriting this or thinking of cosine cubed of x as follows, cosine of x cubed, you'll be able to more easily identify the outer function as x to the third power. And notice by rewriting it like this, you can now easily identify the inner function, which would be cosine of x. So here, g of x would be cosine of x. All right, so again, just make sure you really understand that. At this point in your Calculus 1 course, you're going to start to see powers of trig functions, and I see a lot of common errors due to misinterpreting what this power notation means. All right, now for example 7, this one's a little bit more complicated. We do have an outer power, the 100th power, so let's take our outer function to be x to the 100th power. And our inner function, well, that'll be everything inside parentheses, that fraction or quotient, g of x here, we would take it to be x squared minus 1 divided by x squared plus 1. And there we go. For each of these 7 functions, we've identified an outer function and the corresponding inner function. And notice for all 7 of these examples, all of the outer functions are very simple. And notice they all fit a pattern. All of the outer functions are x raised to a power here. something of the form x to the n. And that's really nice because we know how to differentiate x raised to a power. We would just differentiate these outer functions by using the power rule. And again, that's what's going to make the chain rule very easy to apply if you have a simple outer function. All right, next, let's go ahead and get to some examples with exponential functions. Next up, 5 more examples involving exponential functions. If you want, go ahead and pause the video right now to make an attempt at these. Otherwise, let's go ahead and get right to them. Now, the first thing I want to point out is for an exponential function, something of the form e raised to something, our exponent, that's going to be thought of as the input or inside to the exponential function. So all of these 5 examples, the outer function will be e to the x. So for our first example, our outer function will be e to the x. The inside or inner function, well, that's just going to be the exponent, 2x. So here we would take g of x to be 2x. And that's it. All right, for example 2, very similar. The outer function is again e to the x. And our inner function will be negative 3x plus 4. Hopefully you can see the pattern here. For example 3, the outer function is again e to the x. And the inner function, the exponent, the inside, that's just sine of x. All right, the next example, very similar to the other one, where we have trig functions, but now, while our outer function is still e to the x, our inner function is going to be this product, x times cosine of x. And I want to point out here, eventually when we differentiate this using the chain rule, example 4 is going to be a moderately challenging example. And that's because we're applying the chain rule because we have a composite function, but notice your inner function is a product. So for this example, eventually, when we apply the chain rule, we'd be using the chain rule, but also the product rule. So just be aware of that. Here, we're just identifying the outer and inner functions. All right, and for the final example, example 5 here, we can rewrite this, which is one of our tips for calculating derivatives. Rewrite before you differentiate. And what we can do here is take our 1 over, where we have an exponential in the denominator. We can rewrite this with a negative exponent as e to the negative 3x. And this is nice because you might be tempted to apply the quotient rule here, but by rewriting it, you can apply the chain rule, which is usually much easier. So here, our outer function would again be e to the x, but the inner function, that's now negative 3x. All right, and again, worth pointing out, notice here that simple act of rewriting, we go from applying maybe the quotient rule to now by rewriting it, we apply the chain rule. All right, exponential functions are very important and frequently encountered in Calculus 1 with calculating derivatives and everything for the rest of the course. So make sure you're comfortable identifying the outer functions and inner functions for things like these examples. Next up, let's get to some trig functions. Our next 7 examples all involve trig functions. However, some of them are rather tricky, mainly due to notation. So if you want, go ahead and pause to make an attempt at these 7. Otherwise, let's go ahead and get to it. And again, we'll point out all the common misconceptions which are due to notation here. All right, our first example, this seems really straightforward. We have 4x inside of the cosine function. So we'll identify our outer function as cosine of x and our inner function as 4x. All right, and it's worth pointing out here, you might be writing this cosine of x with parentheses or without. Perfectly fine either way. All right, for example 2, seems very straightforward. We have x squared inside of the sine function, so we would take our outer function as sine of x and our inner function as x squared. And that's it. Now, when I go through the chain rule, I always like to introduce these two examples in class together because they're very similar but very different. Here, notice, we can rewrite this as sine of x squared. And it's somewhat similar to above, however, your outer and inner functions are switched. So for example 3 here, our outer function would be x squared, and our inner function would be sine of x. And again, notice relative to the example above, example 2, same functions, but the role they play for the outer and inner functions is switched or reversed. And that makes a huge difference to how we would calculate the derivative there. All right, next up, example 4. Again, hopefully this is straightforward. We have e to the x now inside of the tangent function. So let's identify our outer function as tangent of x and our inner function as e to the x. All right, and that works. Just, again, be careful here. You don't misinterpret this as multiplication. This is not tangent times e to the x, just like this is not sine times x squared, and that's not cosine times 4x. So just be careful of that. Now with that in mind, this also presents the same error or common misconception. This is not sine times cosine. Here we have cosine of x inside of the sine function. So we would identify here our outer function as sine of x and our inner function as cosine of x. And just be careful of that. I've seen even some really good Calculus 1 students take a look at this and they think I'm going to calculate the derivative by using the product rule. That's not the case. This is a composite function. We would differentiate it using the chain rule. Now let's go ahead and write down what this would look like if this were correctly interpreted as a product. And that would be written correctly as sine of x times cosine of x, like that. And sometimes, just to emphasize that we don't have any inner functions, this might be written as sine of x with parentheses and cosine of x with parentheses, like that. So just be careful of that very common misconception. There is no product here in example 5. This is a composite function. All right, now with that out of the way, let's go to example 6. This also seems straightforward relative to some of the previous examples. Our outer function would now be cosine of x. But our inner function, the inside, is a little more complicated here. This fraction or quotient of exponential functions. The inside function here, g of x, this would be 1 minus e to the 2x divided by 1 plus e to the 2x. And eventually, when we calculate the derivative of a function like this would present a good amount of work. This is a composite, so we'd be using the chain rule, but when we calculate the derivative of our inner function, that's going to require the quotient rule because it's a fraction or quotient. But notice, we still have composites, e to the 2x. So this example involves the chain rule with the quotient rule with the chain rule yet again. We'll be getting to those examples in another video linked down below in the description. All right, our final example here This one's a little bit more complicated, again, just due to power notation. So let's rewrite that. We'll have cotangent of 3x inside and then the fourth power on the outside. And that's going to allow us to easily identify the outer function as x to the fourth, and our inner function would be everything inside, which would be cotangent of 3x. And again, it's also worth pointing out here, eventually when you're asked to differentiate this, this is a composite function, so you'd be using the chain rule, but when you differentiate your inner function, this is again a composite function. So you would use the chain rule yet again. So just make sure you're aware of that. Some of these more complicated examples, like examples 6 and 7, may require multiple applications of the chain rule in combination with product and or quotient rules. All right, now again, all these problems, we were just focusing on identifying the outer function f of x and the inner function g of x. No derivatives were calculated here, but if you're comfortable with these problems, identifying a function as a composite, you should be set to apply the chain rule. Go ahead and check out the video linked down below in the description, where we'll get to applying the chain rule and a bunch of examples. Hope you enjoyed this brief review of composite functions. Hope you're going to be successful with the chain rule. If you're enjoying the content, support the channel, like and subscribe.